Hello everyone, welcome to this, my matching and allocations problem updated for 2024. Why? Because there is so much more to be learned for the Hungarian algorithm, which is pretty much what this is going to deal with later. Now, if you are looking for how to not only minimize allocations, but to maximize and deal with all sorts of what if the matrix is non-square, then this is the video for you. My name is Darren from Maths Guru. Thank you very much for watching. If you can do me the honor, please, of subscribing, it does me the world of good. Why? Well, basically, it just means that people are watching this video, or it lets me know that that is true anyway. Who watches maths videos? Seriously, would you be watching this late at night? No, exactly. So, basically, behind me, you will see the recap of past learning. Now, obviously, we've learned a lot of language already for this course, but there are more and more words. And I think that's what tricks people with general maths. It's the words. It's like, when do I use this? How do I know that? And hopefully my videos are there to help you out. Mathsguru.com. That's my little corner of the interweb. As I've said so many times before, if you head over there, there are all these videos there for you. They are all in order, and hopefully they will help you smash maths. Right, let's have a look. Now, some of the language that we're going to meet now are things like here, that is called a bipartite graph. Now, a bipartite graph is basically where you have two sets of things that you are going to try and allocate. And in this situation, it may well be that you've got two teams, maybe, called the knights and the rookies, or different players on chess teams. And the lines which basically show how we're going to connect or who is going to play whom. So Jenny in this situation is going to play Lisa. Roger is also going to play Lisa. Terry is going to play both George and Karen. And who else? Sharon is going to play Karen. And so basically reading this is awesome. This is a bipartite graph where each edge in the bipartite graph joins one vertex from one group to another vertex in another group. That is it. Bipartite graph, important to know. Put it in your summary book. Then we move on to directed bipartite graphs. Now this is where, I suppose this is a great example, is if you were looking at the idea of a teacher and an instrument, all right? Adrian teaches the piano and the guitar, all right? So that arrow makes sense because it's sort of saying, who teaches what? It would make no sense for the piano to teach Adrian. That I would like to see. It's a whole new Disney video, but maybe in that situation. So we've gone from bipartite graphs now to a directed bipartite graph and then complete bipartite graphs. I'm going to come back to the word weighted at another point because ultimately that would mean that these would have individual weights, and that could be how many things employee one can create per hour, how long it takes them to work per hour, how long it takes them to do a task per hour. There's lots of things that can be done, all right? So in this situation, though, the reason it is complete is because every employee can basically operate every single machine. Now, why on earth would that be useful to us? Well, employee one may well be very good or could use all four of those machines. But what if they're actually faster at machine one? And what about if employee 3 was really good at machine 2 and employee 4 was, well, also good at machine 1, but second good at machine 3? And that was terrible language, I know. Wouldn't it be great if we had some sort of way of being able to allocate people to different tasks? And we do, because that's the whole point of this video. It's called the Hungarian algorithm for a reason. Now, the Hungarian algorithm is basically a set of 7 steps that allow us to allocate, and in this situation, 4 employees to 4 tasks. Now, an important point to note about this is that for the Hungarian algorithm to work, that has to be square. All right, now we're going to put it into a matrix in a moment, and but ultimately this has to be square. It has to have an equal number of tasks and people we're trying to allocate tasks. Now, the Hungarian algorithm is generally used, as I say here, to find the minimum amount of time. But I get messages every single year going, can you use the Hungarian algorithm to maximize tasks? Well, of course you can. And I'm going to show you how a little bit later in this video. But before I go any further, can you subscribe? Yes, that little man in the corner is trying to subscribe. Thank you very much. You can use it to find the maximum, right, but... And I'm really sorry, ClassPad users, but there is actually a UDF, that's what I learned it was called this year, a user-defined function that someone has very kindly written to do the Hungarian algorithm for you. And there was a little bit of a controversy about that this year in the 2024 exam paper, but we'll move on, all right? And this is a screenshot of basically taking the information here And it's not only going to come back with who should be allocated each task, but basically the minimum amount of time it's going to take the employees to conduct each of those tasks. Phenomenally important. Now, for those of you who want to know where to get that program from, it has to be downloaded by your teacher. It is freely available online. If you just put in Hungarian Algorithm Ti-nSpire, undoubtedly the TI website will come up, but you're going to need the teacher to install it onto your calculator through their teacher software. Now, by hand, and you're going to turn around and say, well, hold on a moment. If there is a calculator function, can't I just use the calculator? Well, you could if you didn't have to use or do SACs. Now you're going to turn around and say, huh? The whole point of a SAC is to test your understanding, and there's no way I'm going to put a question on a SAC that is basically allowing you to just put those numbers into your calculator, hit enter, and get an answer, because you haven't really understood what that whole process is. Okay, so these questions are absolutely going to appear on a SAC. All right, if your teachers know anything. Why? Because a lot of people don't even know how to do this. They don't follow the steps. And you're going to say, what steps? And I'm going to go, well, of course, these steps. All right, so there are 7 steps, and you basically work through them section by section until you effectively allocate, and I'm going to sort of explain that in a moment. So if you don't already have the Maths Guru summary book, you can download it from mathsguru.com. It is, I think, pretty good. It's got all of the summary notes I think you're going to need, and it also has a load of VCAA, some of the trickier VCAA questions in it that with answers and sort of hints and tips on how to do well with those as well. All right, so there's the Hungarian algorithm. He says, let's have a look at an example. So the first thing you've got to do is you've got to have an example. So the table below shows 4 employees, Wendy, Xenophon, Yolanda, and Zelda. The machine in a factory are The machines in a factory are represented by the letters A, B, C, and D. The numbers in the table are the times in minutes it takes each employee to finish the task on each machine. So again, every one of these people can operate all of those machines, but we notice that Wendy seems to be pretty quick on machine A. Now, a lot of people trying to say, well, can't I just work this out by trial and error? I can't I just look at it and do it? If you could, then it probably wouldn't be such a big topic in this sort of section of the course. All right, the table is called a cost matrix. In this situation, it's a cost matrix. Why? Because there's a cost. We want Wendy to be quicker at certain tasks, Xenophon, Yolanda, and Zelda. We want them to be pretty quick at each of the tasks. But how do we now do this? Right, well, we're going to go through it step by step, and hopefully I'm not going to make a mistake. If I do make a mistake, I'll put an errata down below, all right? As I'm trying to think out loud and do all of this, apparently in previous years I have made a mistake. Right, let's look at step number 1. What does it say? Subtract the lowest value in each row from every value in each row. So here is a row. Now, sadly, again, when I marked a load of my own student SACs last year, the difference or the lack of understanding between a row and a column was actually quite scary. And a lot of people reduced columns first. The algorithm in your summary book tells you to do row by row. So what I'm now going to do is I'm going to do A, B, C, and D, and I'm going to do W, X, Y, and Z, not Z. Now, what's my lowest value is going to be 30. So for this row, I'm going to take 30 away from each of those values. So 0, 10, 20, and 30. Now I've got a light shining on my screen, so that's going to make life more interesting. Having done that row, what am I going to do now? This row. So I want the smallest value, which is 70, take it away. So, sorry, 40, so take it away. That's going to give me, try again. Did I say 40? Let's try again. 30. My smallest value is 30. So it's going to be 40, 0, 10, and 40. All right, Yolandi, again, which is her smallest. We've got 30 again, to take that away. It's going to give me 30, 20, 30, and 0. And then who have we got next? We've got Zelda, whose lowest is 20. So it's going to become 0, 8, try that one again, 0, 60, 30, and 50. Ka-ching! Now, step number 2, if the minimum number of lines required to cover all the zeros in the table is equal to the number of allocations to be made, jump to step 6. Now, we know there are 4 tasks, so in which case we are looking for 4 allocations. So what this says now is, if you can cover these zeros and use the minimum, the least number of lines to cover those, and the least number of lines is 4, you're done. You don't need to do the Hungarian algorithm before. Now, you could turn around and go, and I'm going to try and do this using a highlighter. You could go, well, there's 1, 2, 3, 4. All right. And yes, that is certainly a way to cover all those zeros, but it's not the one that requires the least number of lines, because actually whenever you have more than 1 0 in a row or a column, you need to try and cover that first. So here we go. So there is going to be 1 line. Here is going to be another, and there is going to be another. So as you can see now, I've covered all of my zeros. The least number of lines I've used is in fact 3, and as such, oh shucks, I now have to continue to the next section of my algorithm. Why? Because only when I have 4 lines can I stop the algorithm.